So for pipe D going into E, we had 19.66 flowing through that pipe, which means going into manhole E, we have 19.66 coming in, and going out, well, there's no additional flow here. So we're going to go out with 19.66 CFS. But why? Why don't we have any additional water going into a manhole? Manholes are there as junction points. So when we have a distance between of pipes that's more than 350 feet, we have to break that up with a manhole for access. This way we can get in there and clean it. Or if you need to change direction on the pipe, it has to be done by creating a joint, and that manhole can basically pick any range of an angle of 0 to 360 to allow that pipe to send water in a different direction. So now we're going to size the pipe going out to the recharge basin. These last pipes in the series tend to be larger because the velocity has to be less. In the next video, after we solve the design, I'm going to talk about why it's so important to keep the flow low at the end of a recharge basin. So on this one, we want to keep the velocity around 3. We want to keep it on the low end, not necessarily down to 2, but around 3. 3 or less is usually good. So let's see. And the reason we want that velocity to float a little bit is it gives us some ability to play with the diameters. Okay. So from a quick look at this, Q is around 19, so 19.66, call it 20 for the graph. My velocity says it's about 3 between a 33 and a 36-inch diameter pipe. So what should we use? We're going to use the 36-inch diameter pipe, and I'm going to tell you why. Not that you need to be concerned about this now, because when you get out into industry, these things may change, but they've stopped making 21-inch diameter pipe. They've stopped making 27, they've stopped making 33, and I don't think they make 39 as well. Basically, every time you want to make one of these pipes, the molds are very expensive, and to stock this stuff just got too expensive. So generally you're going to see 18, 24, 30, 36, and so on. But that shouldn't concern you right now. You can still design. If it's on the nomograph, fair game. There we go, get that back. So what I'm going to do is I'm going to bring it up to 36 inches. 36 inches, which puts my velocity less than 3, but still above 2. 2.8 around, and a slope of about 0.0005, 2.8, 36, and 20. That's what my numbers look like on here. Okay, let's prove it out mathematically. So let's see, we said that the diameter would be 36 inches, which is a pretty good size end pipe to work with. We have a Q of 19.66 CFS. Everything else we're going to solve for. So Q is equal to AV. Velocity will be equal to Q over A. So velocity will be 19.66 CFS over 3 squared pi over 4. So 19.66 divided by 3 squared times pi divided by 4, 2.78 feet per second. I think I said 2.8. So again, we're in that ballpark from the nomograph. Yeah, 2.8. We're close with the nomograph, which is what we're looking for. We take that 2.8, 2.78, go right back into the Manning equation. 1486 r to the 2/3 s to the 1/2 over n. We manipulate that equation, Vn over 1.486 r to the 2/3. Have you memorized this yet? Told you didn't have to, but by hearing me say this over and over and over again, it gets stuck in your head. 2.78 times 0.013 over 1.486 times 3 to the 2/3. So my slope would be equal, oh, squared. That would help. So 3 raised to the 2/3 times 1.486 times 2.78 times 0.013 squared. 0.0001. I thought I came up with a different slope. .001. 0.001's all the way, 0.000. That's all the way here. Something doesn't seem right. Let me look what I did. Oh. Hydraulic radius. 3/4. Okay. Well, I'd like to say that that was on purpose, but first mistake of the semester is on video now. That's why I use the nomograph. The nomograph is going to give you the answer, and you're just making sure it matches. You can catch your mistakes. Let's try this again. 3/4 raised to the 2/3 times 1.486. Inverse that times 2.78 times 0.013 squared. Much better. 0.00086, so we'll round it up to 9. 0.0009. Okay, so that concludes sizing up the pipes for a network diagram, a pipe network. This is just 1, 2, 5 pipes. 1, 2, 3, 4, 5 pipes. If you think about most subdivisions, they can have upwards of 20 or 30 or 40 pipes or more. It's not any more complicated. It just takes more time as you go through it. So what we're going to do now is we're going to put this problem off to the side for now. When I say now, just, we're going to go back to it later on in today's class. But first I want to talk about recharge basins, go through some diagrams of what they look like, how they're constructed, and really what that end section looks like, because that's a pretty important part of what we need to talk about. So I'll close this video down, and the next video will be talking about the recharge basins.